Welcome to the deep dive. So today we're jumping into something that's, well, it's everywhere, invisible, but totally fundamental to how we live now. We're talking about the airwaves.
That's right. Your Wi-Fi at home, your phone connecting to a cell tower, that video streaming seamlessly on your tablet.
All on the airwaves.
Exactly. It all rides on these unseen currents, radio frequency spectrum or RF spectrum.
It's like this huge invisible highway, isn't it?
A massive highway, yeah. Carrying all our digital stuff, our data, our conversations, our connection to, well, everything modern.
But, and this is the kicker, right? This highway, it's not infinite.
Not at all. It's a finite resource, a really valuable one.
And the way we manage it currently, well, that creates some surprisingly big problems that actually affect all of us, from, slow internet speeds to bigger industrial challenges.
That's precisely the core issue. And it's a significant one because despite all the licensing of these RF spectrum bands, companies pay huge amounts for exclusive rights to use certain parts of this highway. A lot of that spectrum is actually underutilized. Massively underutilized sometimes.
Underutilized, so like empty lanes on the highway.
Exactly like empty lanes. This leads to what we call spectrum scarcity. So using your highway analogy, imagine this amazing brand new 12-lane superhighway. But because of maybe outdated rules or just inefficient use, only 2 or 3 lanes are ever actually carrying traffic.
Even if the other 9 or 10 are completely empty.
Completely empty. It creates this massive bottleneck in wireless communication.
Wow.
And it's not just annoying. It's not just an inconvenience. It's a costly resource being wasted. Think about the economic impact.
Yeah, I can imagine. It must stifle innovation, slow things down.
Exactly.
Yeah.
Slower data speeds, limits on new wireless services we could be developing. It's this global inefficiency, really, which is why we desperately need innovative solutions, ways to use what we already have much, much more effectively.
Okay, so the stage is set. We've got this problem of wasted resources. And that, I guess, is where something really clever comes in. Cognitive radio. CR.
Right.
This sounds, well, intelligent. The idea is you have unlicensed users, let's call them secondary users, SUs.
Yep, SUs.
And they don't just sit there waiting for their assigned lane. Instead, they actively, dynamically sort of sniff out and access the licensed bands. But only when the primary users, the licensed ones, aren't actually using them. Is that right?
That's the core concept, opportunistic access.
It's like a super smart parking app for the airwaves.
Ah, that's a great analogy, actually.
Your autonomous car, the SU, knows exactly when a premium spot the licensed band is free. It zips in, uses it, and then gets out the instant the owner, the primary user, comes back.
Exactly. No wasted space, no collisions, ideally.
Yep.
Smart, dynamic sharing.
Okay, sounds brilliant. But for this to work, reliability must be key, right? You can't have these SUs accidentally interfering with the primary users.
Absolutely paramount. Reliability is everything. So for cognitive radio to function reliably, it must know, with extremely high certainty, is a primary user present in this band right now, or is it absent?
Okay.
That crucial step, that act of listening, figuring out if the space is occupied, that's what we call spectrum sensing.
Spectrum sensing, the eyes and ears of the cognitive radio.
Precisely. It's the fundamental awareness system. Yeah. Without accurate spectrum sensing, the whole clever idea kind of falls apart.
Right. You either cause harmful interference, which is bad.
Very bad.
Or you miss opportunities to use free spectrum, which defeats the purpose.
Exactly. It's a tightrope walk.
So how do you actually do this spectrum sensing? What's the mechanism? I gather the standard approach, the sort of go-to for a while, has been energy detection, ED.
That's right. Energy detection has been very common.
Yeah.
And for good reason. It's relatively simple to implement. It's computationally quite light. And importantly, it doesn't need to know anything specific about the primary user signal beforehand.
So how does it work?
Yeah.
Just listening for energy?
Pretty much. You measure the received power or energy in a specific frequency band over a short time. If that energy level pops above a certain preset threshold...
You assume someone's transmitting, a primary user.
Correct. And if it stays below the threshold, you assume it's just background noise. The channel's free.
Simple. But you mentioned earlier, like any simple tool, it's got weaknesses.
Oh, definitely. The real world is messy, especially the wireless world.
Yeah.
ED's simplicity is also its Achilles heel. It's like trying to figure out if someone specific entered a noisy party just by listening to whether the overall volume went up.
You might get a general idea, but you could easily be wrong.
Exactly. You miss the nuances. And those real-world wrenches, as you put it, they seriously degrade ED's performance.
What kind of things are we talking about?
Well, several pervasive wireless channel phenomena, Things like fading.
Fading. That's when the signal strength just drops off suddenly.
Right. It can fluctuate rapidly over short distances or time. It's caused by signals reflecting off buildings, hills, even moving objects, and interfering with each other. Multipath propagation.
Like echoes messing up the sound.
Good analogy. Then there's shadowing.
Shadowing. Like being in the shadow of a building.
Precisely. Large obstacles, buildings, hills, dense trees, they block the signal path. This causes bigger, slower variations in signal strength, creates dead zones where the signal is just really weak or non-existent.
Okay, fading and shadowing makes sense. Those definitely confuse a simple energy detector.
They do. But maybe one of the trickiest ones for a single sensor is the hidden terminal problem.
The hidden terminal problem.
Yeah.
That sounds intriguing. What is that exactly?
Okay, picture this. You're a secondary user, your device is trying to be smart, right?
Right. Listening for the primary user.
But there is a primary user transmitting nearby. Maybe it's, I don't know, a critical radar system or an emergency service radio, something important.
Okay.
But maybe there's a huge building or you're down in an urban canyon between your device and that primary user.
So I can't hear them.
Exactly. Your device simply cannot detect their signal. You're effectively hidden from their transmission.
Okay.
Now, meanwhile, another secondary user, maybe just a few blocks over, can hear the primary user. No problem.
But my device thinks the coast is clear. Because from its perspective, it is.
Precisely. So your device, completely unaware of the active primary user, might decide the spectrum is free and start transmitting.
And boom, interference, even though I didn't mean to.
Exactly. You caused disruptive interference to that potentially critical primary user. Your single pair of eyes just wasn't enough to see the whole picture.
So fading, shattering, hidden terminals, it sounds like relying on just one sensor is pretty unreliable.
It can be very unreliable. These are real-world challenges that fundamentally undermine the cognitive radio concept if you only rely on single-user sensing.
Okay, so if one pair of eyes isn't enough, the logical next step is more eyes working together.
That's the natural evolution, yes. Bring in the team.
And this is where cooperative spectrum sensing, or CSS, comes in.
Exactly. CSS is a really promising solution because it leverages something called spatial diversity.
Spatial diversity, meaning sensors in different locations?
Right. You have multiple secondary users spread out geographically.
Yeah.
Think of it like deploying a whole reconnaissance team instead of just one scout.
Each one sees the situation from a slightly different angle.
Precisely. They all report back, and you pool their intelligence to get a much more complete, much more reliable picture of the environment than any single scout could provide alone.
Makes sense. Many eyes are better than one.
It's not just having more eyes, though. It's about how they work together, how the information is combined.
Right. So how does that typically work in CSS, let's say in a centralized model?
Okay, in a typical centralized CSS setup,
Right.
you have multiple cooperating secondary users, CSUs.
Our recon team.
Exactly. Each CSU is out there sensing the spectrum individually from its unique location. Because they're spread out, they experience different fading, different shadowing effects. One might be in a dead zone, but another might have a clear signal.
So they get diverse perspectives.
They do. Then, each CSU sends its local information, basically its own conclusion about whether the primary user is present or absent, to a central entity.
The command center?
Yep, called the Fusion Center, or FC.
Okay.
The Fusion Center acts like the central brain. It gathers all these individual reports, which might be noisy or even wrong sometimes.
Why? Because of the issues we just discussed.
Exactly.
Yeah.
And then the FTC applies some kind of smart decision-making rule to combine all that information. The goal is to make a final decision about the primary user's presence that's much more robust, much more accurate than any single CSU could achieve on its own.
So it filters out the individual errors, hopefully.
That's the core idea. Leverage the collective to overcome individual weaknesses. Significantly improves detection performance compared to just one user trying to figure it out alone.
Okay, this sounds like a really solid approach. Cooperation overcomes individual limits. Makes perfect sense. But you mentioned earlier there's a twist. An elephant in the room that early studies maybe didn't fully account for.
Yes. Here's where it gets really interesting and where our deep dive really begins.
Okay, I'm ready.
Many earlier studies on CSS, brilliant as they were, often made a crucial simplifying assumption. A very convenient one, perhaps too convenient.
Which was?
They assumed that the communication channels between the cooperating secondary users and the Fusion Center were perfect, error-free.
Wait, the channels carrying the ones and news from the scouts to the command center? They assumed those were perfect.
Often, yes. Or they didn't explicitly model the errors on those links.
Hang on, those are wireless channels too, aren't they?
The Gingo. That's the critical oversight.
They're not magic fiber optic cables connecting everyone.
Not at all. They're subject to the very same fading, shadowing, noise, and interference that plague the initial sensing by the CSUs in the first place.
Wow. Okay. So the problem we're trying to solve with cooperation
Yeah.
also affects the cooperation mechanism itself.
Precisely. It's a hidden vulnerability in the system design if you don't account for it.
So this is the core challenge we're digging into today. What happens when these reporting channels, the links carrying the votes, are themselves unreliable?
Exactly. What is the actual impact? How much does performance degrade when those ones sometimes slip to nairs and nairs slip to ones on their way to the fusion center?
And, more importantly, can we fix it? Can we overcome these imperfect reporting channels?
That's the mission for you today.
Yep.
We're going to analyze just how bad that performance degradation is. And then, and this is the exciting part, we'll present an algorithm, a method based on channel coding.
Channel coding, like error correction.
Exactly like error correction. An algorithm that can not only significantly improve the performance in the face of these errors, but, quite remarkably, under certain conditions, can even completely remove the negative effects of those reporting channel errors.
Completely remove them. Wow. Okay, now I'm really hooked. Let's get into it.
The foundation, how cooperative sensing works and where it breaks down.
All right, so let's build this up properly. We need to understand the baseline first, right? How this cooperative spectrum sensing is supposed to work, assuming for a moment those perfect reporting channels, before we break it.
Good idea. Lay the foundation first.
So the basic setup, we have, say, M cooperating secondary users, MCSUs, all working together.
A team of M sensors.
And each one, let's call a specific one CSUI, is listening to a particular frequency band, trying to figure out if the primary user, the licensed owner, is transmitting.
That's the core task for each CSU, listening carefully. And fundamentally, each one is trying to decide between two possibilities, two hypotheses.
Right, you mentioned H0 and H1 earlier.
Correct. H0 is the hypothesis that the primary channel is free.
Clear.
Nothing there but background noise.
Just static, basically.
Pretty much, yeah.
Right.
Random noise. And H1 is the hypothesis that the primary channel is occupied, meaning the primary user's signal is present, along with the noise.
So signal plus noise, H0 is noise only, H1 is signal plus noise. That's the basic decision.
That's the fundamental decision each CSU is trying to make, yes. Is it just noise, or is there a signal buried in there?
Okay, so how does an individual CSU, CSUI actually make that call between H0 and H1? You said it uses energy detection, so it measures the energy it receives.
Exactly. It calculates the energy of the signal it receives over a specific observation time. This energy value is its raw measurement, its decision statistic. Let's call it T.
T, okay.
Then it compares this measured energy T to a predefined level, a threshold. We often call it tau.
A threshold, like a tripwire.
Good way to put it. If the energy P is above the threshold,
It assumes this signal is strong enough to be the primary user. So, H1, reporter 1.
correct, it decides 1, indicating primary user present. If the energy 2 is below the threshold,
It assumes it's just noise. H0, reporter 0.
exactly, it decides 0, indicating primary user absent. It's a simple binary decision based on that energy level.
And this simple 1 or 0 output, that's what you called hard combining earlier.
Yes, this is a form of hard combining or hard decision fusion. The CSUs send just these binary decisions, the ones and news, to the fusion center.
Not the actual energy levels.
No, not in this basic hard combining scheme.
Yeah.
Sending just one bit, well, 1 or 0, is very efficient in terms of bandwidth needed for the reporting channels.
Ah, okay. Less data to send back to the FAC. Makes sense.
It minimizes the overhead. It's like the scouts sending back a simple thumbs up or thumbs down, not a detailed report.
Got it. So all these ones and news, these thumbs ups and thumbs downs, arrive at the fusion center from all MCSUs. What does the FEC do with this collection of votes? It's the grand decision maker, right?
It is. The FCC aggregates, or gathers, all these M binary decisions. And then it applies a fusion rule to make the final overall decision. A very common and effective rule is the K out of M rule.
K out of M, so like a majority vote, but maybe not strictly majority.
Exactly. It doesn't have to be a simple majority. K is a parameter you can set. The rule is if at least K out of the MCSUs report a 1, meaning they think the PU is present.
Then the fusion center declares the channel occupied.
Correct. Only if the number of ones received is K or more does the FC make the final decision of H1. Otherwise, it decides H0 sick, channel free.
So it's a voting system. You need at least K votes for guilty, otherwise it's not guilty.
That's a perfect analogy. It's a consensus mechanism. And choosing the value of K is important. It determines the trade-off.
How so?
Well, if you set K1, that's like an OR rule. If any single CSU reports a 1, the FEC declares the channel busy.
Very sensitive, but maybe prone to false alarms if one CSU makes a mistake.
Exactly. High probability of detection. Potentially high probability of false alarm. On the other hand, if you set KM, that's an AND rule, all CSUs must report 1.
Much harder to get a yes vote. So fewer false alarms, but you might miss the PU if even one CSU fails to detect it.
Precisely. Lower false alarm rate, but potentially lower detection rate, too.
Yeah.
So the system designer has to choose K carefully based on the application's needs. How critical is it to avoid interference versus maximizing spectrum access? It's a crucial tuning knob.
Okay, that makes sense.
Oh.
So the K out of M rule at the FC combines the simple 1-0 votes from the CSUs to get a more reliable overall decision than any single CSU could make.
That's the goal, yes.
Yeah.
Leveraging cooperation to improve reliability.
Right. Assuming those votes arrive correctly at the FEC.
Ah, yes. Back to the hidden flaw.
The assumption of error-free reporting channels. We said earlier that's often where the model stopped.
There's a common simplification in early work, yeah. Assuming that the 1 sent by a CSU is always received as a 1 by the FC, and a 0 always arrives as a 0.
But let's unpack this again because it's critical. These reporting channels, they're wireless.
They are indeed wireless links in most practical scenarios.
So they suffer from the exact same problems that made us need cooperation in the first place. Fading, shadowing, noise.
Exactly the same phenomena. The physics doesn't change just because it's a reporting link instead of the primary user link.
So the consequences, the CSU's vote, its detection result, can get corrupted on the way to the fusion center.
Precisely. A 1 might flip to a 0 might flip to a 1. The FEC receives a potentially corrupted version of what the CSU actually decided.
It's like the voting slips getting smudged or misread before the final count.
Excellent analogy. And this is where the binary symmetric channel, or BSC model, comes in handy. It's a simple but effective way to represent this corruption.
Okay, BSC model. How does that work?
Imagine each bit,
Yeah.
1 or 0, meant from a CSU to the FSC, passes through this abstract channel, the BSC. This channel has one key parameter, P, the probability of error.
P, error probability.
Right. It represents the chance that a bit gets flipped during transmission. So if a CSU sends a 1, it arrives as a 0 with probability P. If it sends a 0, it arrives as a 1 with the same probability P.
Symmetric because the flip probability is the same in both directions.
Exactly.
Yeah.
It's a simple model, but it captures the essence of the problem. The reporting links are unreliable, and there's a quantifiable chance, P, that the information received by the FEC is wrong.
And this P, this error probability, is the core problem we need to tackle because it directly messes up the K out of M rule, right? The FEC might be counting flipped votes.
It absolutely does. It undermines the integrity of the cooperative decision.
Yeah.
The FCSC might make the wrong final call, not because the CSUs sensed incorrectly, but because their reports got garbled in transit. This is the performance degradation we need to fix.
The innovation A repetition code to the rescue.
Okay, so problem clearly defined. Cooperative sensing is great, but the wireless reporting channels between the CSUs and the fusion center are noisy, causing errors, and messing up the final decision.
That's the crux of it, yes.
So how do we fix this? You mentioned channel coding.
Right. Channel coding is a whole field within communication theory dedicated to making transmissions more robust against noise and errors. It's a standard toolkit for reliable wireless comms.
And the basic idea is adding redundancy, making the message more robust so it can survive some errors.
That's a key principle, yes. Add structured redundancy so the receiver can figure out the original message even if parts of it get corrupted. And specifically, we look at error correcting codes. These are really powerful. They don't just tell you if an error happened, like error detection codes. They can often correct the errors, reconstructing the original data.
Okay. Correction is better than just detection here.
Definitely. And the simplest form of error correcting code, conceptually at least, is a repetition code.
Repetition code.
Yeah.
Sounds simple. Just repeat the message.
That's exactly what it is. It's beautifully simple, but as we'll see, remarkably effective for this specific problem of corrupted CSU reports.
Okay, so this leads us to the proposed algorithm. Algorithm 1, you called it. How does adding simple repetition fix the P problem? Let's walk through it.
All right, step by step. Step 1. CSU local decision. This part stays exactly the same as before.
Okay, so each CSUI still listens, computes its energy tie, compares it to the threshold, and makes its own local decision. 1 PU present or 0 PU absent.
Correct. The initial sensing part doesn't change. The local intelligence is still gathered in the same way.
Got it. Step 2. This must be where the repetition comes in.
This is the key innovation. Step 2, repeating the message. Instead of sending just that single 1 or 0, each CSU repeats its decision bit R times.
R times. So R is the repetition length.
Exactly. R is how many times you send the same bit. For example, let's say a CSU decides H1, so its decision is 1. And let's say we choose R equals 3.
Okay, repeat it 3 times.
So instead of sending just 1, the CSU transmits the sequence 111 to the fusion center.
And if it decided 0?
It would send 000.
Literally just sending the same bit multiple times. Yeah. Seems almost too simple.
It does seem simple, but remember the BSC model for the reporting channel. Each of those transmitted bits has a probability P of being flipped independently.
Ah, okay. So sending 111 doesn't guarantee the FC receives 111.
Not at all. If P is, say, 0.1, the FC might receive 1011 or 011, or maybe even 011 if 2 bits get flipped. But the chance of all 3 flipping, receiving 000 when 111 was sent, becomes much smaller, especially if P is reasonably low.
Right. It gives the correct bit multiple chances to get through the noise. Redundancy buys robustness.
Precisely.
Okay, so the CSU sends its repeated decision, a 111 or 000 E543. What happens at the fusion center? That's step 3.
Step 3, FC's majority decision per CSU. This is crucial. The FC receives the sequence of R bits from each CSU. Let's stick with R3. So from CSU 1, it might receive, say, 1, 0. 1 from CSU 2, maybe 0, 0, 0. From CSU 3, maybe 1, 1, 1.
Okay, sequences of potentially corrupted bits arrive.
Now, before combining the decisions from different CSUs, the FC first decodes the message from each individual CSU using a majority rule.
A majority vote on the repeated bits for each scout's report.
Exactly. Let's take CSU 1, which sent 11-1, but the FC received 1-0-1. The FC looks at 1-0-1. How many ones? 2. How many zeros? 1.
1 wins the majority.
So the FC decides that CSU 1's intended message was 1. It corrects the single bit error.
Okay. What if CSU 2 sends 000 and the FC received 010?
Same process. Received 010, 2 zeros, 0, 0, 0, 0.
0 wins the majority. FC decides CSU2 intended 0. Another correction.
Right. This majority decision on the received repeated bits for each CSU acts as the first layer of error correction. It cleans up the individual reports before they are used in the cooperative decision.
Very clever. It uses the redundancy to filter out the channel noise effects for each CSU's contribution.
It effectively reduces the probability that the FC misunderstands what a specific CSU decided. The effective error rate for each CSU's report becomes much lower than the raw channel B.
Okay, so now the FC has a set of corrected decisions, 1 for each CSU. What's the final step? Step 4.
Step 4. FC's final cooperative decision. Now that the FC has these cleaned up, more reliable individual decisions, let's call them the decoded decisions, D1, D2, DM, it applies the same K out of M rule as before.
Ah, okay. So it counts how many of these corrected decisions are 1.
Exactly. It counts the number of ones among D1 to DM if that count is K or more.
It declares the primary user present, H1, otherwise absent, H0.
Correct. So it's a 2-stage decision process. First, use majority logic on repetitions to clean up each individual CSU's report. Second, use the K out of M rule on those cleaned up reports to make the final cooperative decision.
That simple addition of repetition combined with majority logic at the FC for each CSU seems like a really elegant way to combat those reporting channel errors.
It is elegant, and as the results show, surprisingly powerful.
The scientific proof unpacking the performance results.
All right, the algorithm sounds neat, simple repetition, majority logic. Elegant. But the proof is in the pudding, right? Does it actually work? How well does it combat those errors?
Absolutely. Theory is nice, but we need evidence. And that comes from performance analysis and simulations.
And how do we measure performance here? You mentioned 2 key metrics earlier.
Yes, the 2 critical metrics for spectrum sensing are the probability of false alarm, Q, and the probability of detection, QD.
Remind us quickly what they are.
Q, false alarm. That's the probability the system says the primary user is present, H1, when in fact the channel is free, H0.
Saying intruder when there's no one there. Bad, because it wastes spectrum opportunities.
Precisely. We want Q to be as low as possible. Typically, cognitive radio systems have a strict target for Q. QD detection, that's the probability that the system correctly says the primary user is present, H1, when it really is present, H1.
Well, correctly catching the intruder. Good, because it protects the primary user from interference.
Exactly. We want Q to be as high as possible, given a certain low target for Q. It's always a trade-off.
High Q, low Q.
Yeah.
That's the goal.
That's the goal. And importantly, our analysis shows that the theoretical calculations we derive for Q and Q for this system, they align perfectly with results from Monte Carlo simulations. You can see this in Figure 3 from the source material.
Monte Carlo simulations, that's like running the scenario computationally thousands, millions of times with random noise and errors.
Exactly. It's a way to statistically verify the theoretical math by simulating the random real-world processes.
And the fact that they match perfectly gives us confidence.
Immense confidence. It means our mathematical model accurately captures the behavior of the system, including the effects of errors and the proposed solution. What the math predicts, the simulation confirms.
Okay, good. So let's look at the results. First, scenario 1. Just how bad is the impact of those imperfect reporting channels without the repetition canard?
Right. Establish the baseline problem. Figure 4 and table bar and free. I really highlight this.
What do they show?
They show a stark reality. As the probability of error, P, on those reporting channels increases, the detection performance, QD, of standard cooperative spectrum sensing degrades significantly.
How significantly? Give us some numbers.
Okay, let's take a specific operating point. If we compare the detection probability Q when P is 0.1 versus when P is 0.2, the Q with P equals 0.2 is 21.49% lower than with P is 0.1.
Wow, almost 22% worse performance just because the error rate doubled from 10% to 20%.
It's a substantial drop.
Yeah.
And it gets worse. Compare P.3 to P equivalent 0.1. There's a massive 55.45% degradation in QD.
Over half the detection capability is lost if the reporting channel error rate hits 30%.
Yes. This isn't a minor dip. It's a critical blow to the system's reliability. It shows that ignoring reporting channel errors gives a wildly optimistic view of performance.
Yeah.
The basic CSS system is very vulnerable to these errors.
Okay, that paints a pretty grim picture for standard CSS in realistic conditions. But now, scenario 2, the good news. What happens when we apply the proposed algorithm, the repetition code?
Now for the turnaround. Figure 5 and Table 2 demonstrate the power of the repetition code.
What are we seeing there?
We're seeing significant improvement in Q as we increase the repetition length R, even with the same underlying reporting channel error P.
So more repetitions equals better performance.
Definitely. Let's look at the numbers again, maybe for a target false alarm rate of QF equals 0.01. The value of QE when we use just 3 repetitions, R3, is 123.67% higher than using no repetition, R equals 1, which is the standard CSS case.
Whoa, more than double the detection probability just by repeating the bit 3 times.
That's right, a massive improvement. And it continues, though, with diminishing returns. Going from R equals 3 to R equals 5 gives another 16.36% increase in Q rate.
So even small amounts of repetition make a huge difference.
A huge practical difference.
And you mentioned something even more remarkable, that performance can actually saturate.
Yes, this is the really fascinating part. What the results show is that if you keep increasing R, the performance, QD for a given Q, of our proposed algorithm running over the imperfect channel, it actually converges, it saturates to the performance level you would get from standard CSS operating over a perfect, error-free reporting channel.
Wait, so adding enough repetition makes the performance as good as if there were no reporting errors at all. It completely removes the effect of P.
That's exactly what the results indicate. The repetition code, combined with the majority logic, effectively cleans up the channel errors to the point where they no longer impact the final decision, provided R is large enough.
That's incredible. It's like noise cancellation for the reporting channel.
It is. Look at Table 2 again. For the parameters used there, the value of QD saturated to 0.3010 when R reached 7.
And increasing R further to 9 didn't improve it.
Didn't change it. It had already reached the performance limit set by the perfect channel scenario.
So in that case, R7 was enough to completely eliminate the impact of the reporting channel errors.
Correct. A minimal amount of repetition buys you back the performance you lost due to the imperfect channel. That's the core finding.
Okay, let's visualize this. Scenario 3. A direct comparison, Figure 6.
Figure 6 puts it all together beautifully. It plots the ROC curves. It's QD versus Q.
And we see 3 curves.
Yes. The top curve, the best performance, is standard CSS, assuming a perfect reporting channel, P equals 0, 0. This is the ideal theoretical limit. The bottom curve, much lower, shows the performance of standard CSS when the reporting channel is imperfect. Here, P 0.1, and there's no repetition code, R1. That's the degraded performance we talked about.
Okay, ideal versus degraded reality.
And then there's the third curve, representing our proposed algorithm using R key 5 repetitions, running on that same imperfect channel, P equal 0.1.
And where does that curve lie?
It lies almost exactly on top of the perfect channel curve.
Wow. So with just 5 repetitions in this case, the algorithm running on the noisy channel performs almost identically to the ideal system with a perfect channel.
Precisely. It visually confirms that the repetition code is incredibly effective at overcoming the channel impairments. It practically closes that gap between the ideal and the realistically achievable performance.
That's very compelling visual proof, but it raises a practical question. You said R7 was enough in one case, R5 looked great in figure 6. How much repetition R do you actually need? Does it depend on how bad the channel is?
Excellent question. And yes, it absolutely depends on the channel error probability P. Figure 7 explores this.
What does figure 7 tell us?
It shows the value of R required to achieve performance very close to the perfect channel case for different values of P, and the trend is clear. Higher repetition length is needed in case of high error probability.
So the worse the reporting channel, higher P, the more times you need to repeat the bit R to clean it up effectively.
Exactly. If P is low, maybe R3 or R5 is enough. If P is high, you might need R7, R9, or even more to reach that saturation point, that perfect channel performance level.
It's a direct trade-off. More noise needs more redundancy. Makes sense.
It does. It gives system designers a knob to turn R based on the expected or measured quality of the reporting channels. You can adapt the level of redundancy needed.
Okay, one last scenario check. What about really tough conditions? Not just noisy reporting channels, but when the primary signal itself is very weak, low signal-to-noise ratio, low SNR, does the algorithm still help then?
That's another critical test. Does it help when the initial sensing is already difficult? Figure 8 addresses this.
And the verdict?
The verdict is very positive. The proposed algorithm provides a significant improvement in the detection performance, even at very low SNR ranges.
Even when the signal is barely there to begin with?
Yes. Let's take an extreme example from the figure. An SNR of negative 15 dB. That's a signal buried deep in noise, very hard to detect reliably.
Okay, negative 15 dB. What's the Q?
For the proposed algorithm with repetition, the Q is 0.1344. For the standard CSS algorithm, no repetition, same noisy reporting channel, the Q is only 0.0687.
Let me do the math. 0.1344 versus 0.0687. That's almost double.
Actually, it's 195.62% higher.
Wow, so the repetition code nearly triples the detection probability in this incredibly challenging low SNR scenario.
It does. This shows the algorithm isn't just fixing the reporting channel issue, it's synergizing with the cooperative sensing to significantly boost performance, especially when conditions are toughest. It helps most where help is needed most.
That's incredibly impressive. Robustness even in the worst conditions. Outro. Okay, let's take a breath and recap this. We've been on quite a journey today. We started with this fundamental issue. Our precious radio spectrum, these invisible highways, often being underused because of how we license them. Static lanes, many left empty.
Leading to artificial scarcity.
Then we saw cognitive radio as this really smart solution let secondary users dynamically use the empty lanes.
Opportunistic access.
But for that to work, you need reliable spectrum sensing. Knowing if the lane owner, the primary user, is actually there.
Crucial.
Energy detection alone is too simple, too vulnerable to noise, fading, and especially that hidden terminal problem.
Individual sensing isn't robust enough.
So cooperative spectrum sensing came along. Get multiple users, CSUs, to sense and report to a fusion center. Use a K out of M vote, strengthen numbers.
Leverage spatial diversity, combine information.
But then we hit the hidden flaw. The reporting channels, CSU to FC, are also wireless and imperfect. Errors creep in, corrupting the votes. P0 performance plummets.
The cooperation mechanism itself was vulnerable?
And then we unveiled the solution. This elegant algorithm using simple repetition codes. Each CSU repeats its 1 or 0 vote R times. The FC uses majority logic on the repetitions for each CSU before the final K out of M tally.
A two-stage correction and decision process.
And the results were, frankly, stunning.
They really were. Let's summarize the key takeaways for everyone listening. First, we established clearly the performance of cooperative spectrum sensing is significantly hammered by reporting channel errors. Ignoring them is not realistic.
The degradation was huge, over 50% in some cases.
But second, and this is the breakthrough, a channel coding approach, specifically using a simple repetition code, effectively overcomes these errors.
And how effectively?
2 main points here. 1, using just a minimal number of repetitions,
Hmm.
can essentially remove the impact of reporting channel errors, bringing performance back up to the level of a perfect, error-free channel.
Getting ideal performance from a non-ideal channel.
Exactly. And two, this algorithm provides a really significant boost in detection performance, QAD, especially in those challenging low signal-to-noise ratio conditions where reliable detection is hardest.
So it fixes the reporting errors and helps overall detection, especially when things are tough.
That's the bottom line. More reliable and efficient spectrum sharing becomes possible even in messy, real-world wireless environments.
So what does this all mean for you listening right now? Maybe you're not designing cognitive radio systems, but think beyond just wireless communication for a second. The core problem here was information getting corrupted, getting misinterpreted between multiple distributed sources and a central point trying to make a reliable decision based on that input.
That's a really important point. This isn't just about radio waves. If we connect this to the bigger picture, think about how strategies like this, adding some structured redundancy, using simple consensus rules like majority voting to filter out noise or errors, might apply elsewhere. Where else do we have distributed information gathering feeding into a central decision process where the reporting channels might be imperfect?
Yeah, where else does information get noisy or corrupted on its way to being processed?
Maybe large-scale environmental sensor networks. Each sensor reading might have some noise or error. Could simple averaging or voting improve the overall picture of, say, climate change indicators?
Or what about, say, financial markets? Lots of noisy data points, analysts trying to make sense of it.
Or even think about biology, how cells communicate, how signals propagate through neural pathways. There's noise inherent in those systems too. Could nature be using similar principles of redundancy and consensus?
So the provocative thought for you is, what other imperfect reporting channels exist in complex systems all around us?
And how might these fundamental principles, using redundancy, using consensus mechanisms like majority rules inspired by something as simple as a repetition code, help improve the reliability, the accuracy, and the robustness of decision-making in those other domains?
It's a fascinating question about how to get reliable answers from unreliable information. Something to definitely mull over. That's all the time we have for this deep dive. Thanks for joining us.